This video will be on section 5.4, Riemann sums and the definite integral. So what we'll do is we'll look at what a Riemann sum is, visualize it, and then what we'll see is that it's actually related to an idea that we've been studying, an integral, but it's called a definite integral. I wrote definition twice, probably wrote it too fast. And in this section at least, we're not going to be doing any calculus. We're just going to be approximating areas using rectangles, because that's what Riemann sums are. Right, but we will see in next section when we actually do definite integrals, it's going to be much the same way we did indefinite integrals, with one little thing at the end to adjust. Right, but the definition here says let f be a continuous function on the interval a to b, closed interval. Then the definite integral of f from a to b, the notation for that, it looks like the indefinite integral, but you have numbers on here from a on the bottom to b on the top, represent the area between the graph of y equals f of x and the x-axis from a to b. So once again, I'll draw a visualization of what this means. So let's say we have our graph. Say it looks like that. Y equals f of x looks like that. And then we're only looking from a to b. You can talk about area being above and below and all that stuff, but just the easiest visualization is only looking at if the area is above for now when we start. So if we're looking at the integral from a to b, what we're actually going to compute in next section and approximate in this section is the following. Think about having vertical lines stopping and starting our area here at a and b. Then the area, the shape of this area, if you computed the area like you did with a formula with a circle pi r squared, something, what the definite integral represents is this area. Right. The reason why this is so useful is because what we'll be able to do going forward is actually figure out areas of kind of weird shapes. So you have formulas for areas of a circle, of a square, rectangle, triangle, all those perfect quote-unquote shapes. But if you have like a parabola or e to the x, ln of x, some strange shape, and you want to figure out an area involving that, you do it with integration. And so this is what the definite integral represents. And we'll start with just, well, actually, before we get to the problem, let me add in a little comment. So the definite integral is almost exactly like area. But there is one catch. If the region you want to find the area of is below the x-axis, then the area the definite integral is negative. Right, so if this area, if we computed this area for a graph like this, it would be positive. If we wanted to find the area of a section below, when we do our definite integral, it would be negative. And that's very different from any areas you would find before, because we don't like to think about area being different. So the definite integral is almost the same, but very, very slightly different. But we'll just practice just looking at a graph, being told some areas, and how to figure some stuff out. So this says for the given pictures below and the indicated area. So what it's saying is area A in yellow is 1.258, area B in red is 2.28, and so on. Evaluate the definite integrals below. Now, if it's a little tiny for you, the x values are marked off. So this is x equals a, this is x equals b, the y-axis is where x equals 0. Then we have this is where x equals c, and this is where x equals d at the end. All right, so the first thing you want to do is really just interpret this in words since you might be very new to it. It says we want to figure out the integral from a to b of f of x dx. So in words, we want the area between x equals a and x equals b. If we look at the x values between a and b, that is region A in yellow. And the area of region A is 1.258. Since it is above the x-axis, it stays positive. But that's all there is to that part. Now part B, we want to find the integral from b to 0 of f of x dx. In words, what we're asking right now is we want the area between x equals b and x equals 0. If you look at the graph here, that's region B. From B to 0 is the red region B. And notice the area here of region B is 2.82, but because it's below the x-axis, it's actually negative. And so just kind of seeing how that works. All right, and part C, we want the integral from b to c of f of x dx. So from b to c is going to involve two regions because we're starting here and we're going all the way to c over here. So we want the area of region B and C. Now the area of region A is 2.82, or sorry, B, and the area of region C is 5.899. Right, so let me just go ahead and write in above just to remind everyone. The 2.82 came from region B. The 5.899 came from the region C. But what do we have to do? We have to make sure, since region B is below the x-axis, that it is negative. C is above the x-axis, so we'll keep it positive. But once you get all the positive negatives switched out, this one we have to do a little bit of arithmetic. Oops. So negative 2.82 plus 5.899 gives us 3.079. And that would be our answer for this one. Now, none of these are necessarily drawn to scale, so, region C looks a lot bigger than region B, but if the numbers, region B's area was bigger than region C, you get a negative. So don't worry about the scaling of the picture at all. And I think that's what this last one I did here is for on purpose. So the last one, we want to integrate from 0 to D, starting at 0 and ending at D, so regions C and D. And region C has area 5.899. Region D has area 6.644. And then region D is below the x-axis, so that gets a negative. And so that's from D, and the other one was from C. And then, once again, once you get all those situated, the pluses and the minuses, do it in our calculator. 5.899 minus 6.644, that equals negative 0.745. All right, so once again, it's not necessarily drawn to scale. Certainly region C looks a lot bigger than region D, but because of the numbers they gave us, it turned out to be negative, and that's all right. All right, but very important, once again, definite intervals are a lot like area, but it can be negative because if it's below the x-axis more than the above the x-axis, it's going to be negative. All right, so to begin to understand Riemann sums, begin to understand how the definite interval actually works, in next section we do something called a Riemann sum. And I'll just kind of draw the similar picture that I drew before. Say we have our graph looks like this. And we have A and B. So just easiest to look at it above. But instead of looking at the area altogether, we want to break our area down into rectangles. So let's say I wanted to break the area into 4 rectangles. What I would do is choose 3 numbers between A and B. I'll just call them, what's a good letter? C1, C2, and C3. So it's going to make 4 rectangles. I'm going to draw in dashed lines. And then what's going to happen in Riemann sums is you'll be given a number in each interval, meaning one number in between all of these to plug in to represent the height of your function. The height of the rectangle, I mean. And once again, you don't have to memorize this, but this is just going to explain where the definite interval actually comes from. So what you do is you trace this up to where you hit the graph, and then just draw it straight left and right. And that makes 1 rectangle. And then above, do the same thing for each one. Once again, this is just a visualization. You're not going to have to do this every time you do a problem. And we got our third interval here. That's rectangles at that height. And then the first one, I kind of went in reverse order, but a rectangle would be of height here. And here we would have 4 rectangles. Since we know how to find the area of rectangles, what we would do is find the area of each rectangle and add them up. And that is what the Riemann sum is. Okay. Now, the reason why this figures out our area is the more and more rectangles you have. So imagine we have 10 rectangles. What will happen is the areas will be closer and closer, so we won't have so much hanging above. Like we have extra area here, and we're also missing some area here. And what I'm going to actually do is show you the Wikipedia page so it can explain it a lot easier than me trying to draw more pictures. So this picture here gives you a good description. You don't have to read down here. But what this is doing is you have your function in black, and what they're doing is this first one has 4 rectangles. They're choosing their heights to be just at the right side of the rectangle, but that doesn't matter. And you can see this first one here has too much area. It's got an overestimation. The second one here, it's missing a lot, so it's going to way undershoot it. And overall, it's just completely off. Well, as you go and add more and more rectangles, you'll notice that there's less and less missing area. There's less and less extra area. And by the time you get down to the blue, not blue, this is yellow. By the time you get down to the yellow one here, the amount of rectangles, I'm not sure. Let's just say it's 20 because I'm not going to count them, but you can see that it's a lot closer. We have barely any missing area over here. We have barely any extra area over here. We have barely missing any area and extra area. So it's very much helpful. Now you could only imagine if we had like 1,000 rectangles. We would never want to draw that, but with just 20 we're so close. With 1,000 we would be almost perfect. And the idea with the definite integral is it's actually a limit as the number of rectangles will go to infinity. So it's got some calculus behind it. That's why we will do this integration when we figure out areas and definite integrals. Right, but just wanted you to see that. Before we get to the next section and actually do them, we're going to use the formula, the idea of the Riemann sums here to figure out and estimate the areas. So the definition here of the Riemann sum in the formula looks kind of overwhelming, but it's not too bad. Typically, to make our lives easier, what they do is we'll make the length of each rectangle, or the width, whatever you want to call the bottom side, the same. So if they're all length 1, when we do length times width on each rectangle, we only have to do 1, and then we can add up all the heights. So that's what this messy formula is going to say here. It says, let f be a continuous function on the interval a to b, partition a to b into n subintervals of equal length, and let c sub k represent a number in each subinterval. So that's why I have my c1, or actually I used it kind of opposites, but this would be inside like our c1, our c2, our c3, and so on. Then the formula, the area, if you add them all together, the b minus a over n, this is the width or the base of the rectangle. Since they're all the same, what we do is we factor it out and we compute it once. And then the inside, all we're saying here is evaluate the function at all the numbers given and add them together. This will give us all the heights added together. Right. So one thing I think, I'm not going to redraw because I already drew a picture above here to kind of explain it. But one thing I will say is when you work these Riemann sum problems, you'll be given all the information, but it can be a little overwhelming. It can seem a little overwhelming. So you just want to make sure that you think of it, the formula, in these kinds of words. All right, but I have two examples here. So number 1 says, calculate the indicated Riemann sum S sub 3 for the function f of x equals x squared minus 8x minus 9. What it says to do is partition the interval from 0 to 6 into 3 subintervals of equal length, and let C1, C2, and C3 be those numbers. C1 is 1.2, C2 is 3.4, C3 is 4.5. All right, so the first thing I want to do is b minus a over n, the width of the rectangle. Okay, now n is the number of subintervals, so that is 3. And a and b are the endpoints on the interval here. So a is 0 and b is 6. So we got 6 minus 0 over 3, which simplifies to 2. Okay. Now the part in orange back here, it's telling us what numbers to plug in for the function. Now I will mention, like I said at the beginning of the section, there is no calculus. You're not going to do the derivative. You're not going to integrate. You're just going to plug these into the function. So we're going to plug in 1.2. We're going to plug in 3.4. We're going to plug in 4.5 to our f of x. All right, so x squared minus 8x minus 9, plug in 1.2. And I honestly don't know why these problems, they pick such nasty decimals, but it's the way a lot of them are. Well, we got our calculator for us. That'll make life a little easier. We got 1.2 squared minus 8 times 1.2 minus 9. We get negative 17.16. Now you don't need to worry about graphing this negative or positive, anything like that, because the formula does the work for you. So 3.4, we want to plug in 3.4 for x. We get 3.4 squared minus 8 times 3.4 minus 9. And what does that give us? Negative 1.52. I knew that didn't seem right. I added in a 3 at the beginning. Negative 24.64. That seems a lot more right. And then the last number we want to plug in is 4.5. And I'm going to use that shortcut I used before on some things and just replace the 3.4s with 4.5s. We get negative 24.75. Right, so we evaluate the function at all of these values, add them up. Right, what we're figuring out now, we have this part, which is 2. Now we're adding all the function values up. So let's go ahead and do that. Negative 17.16 plus a negative, so minus 24.64 plus another negative 24.75. We get negative 66.55. Okay. And now that we got this number, multiply by the width, which is 2 in this problem, and we get our answer. All right, so negative 66.55 times 2, negative 133.1. That is the Riemann sum. All right, now do keep in mind that the problem does have to tell you n. You don't have to guess it. You'll see in the next one that it doesn't say s of whatever number. It says s of n. But n is the number of subintervals. Okay. All right, now you can also check that as far as the c values go, they make sense, because if you partition 0 to 6 into 3 equal lengths, the first one would be from 0 to 2, that's where 1.2 fits. The second one would be from 2 to 4, which is where 3.4 fits. And the third one would be from 4 to 6, which is where 4.5 fits. But once again, you really want to focus on, in this section, you're not doing any calculus. And when you compute the Riemann sums, plug in the function values given, add them all together, and then multiply by the b minus a over n. All right, so number 2 here, it's done the same way, but I have found that some people get a little tripped up with the c values because of the way the intervals are, so I want to address that. But it says calculate the indicated Riemann sum S sub n for the function f of x equals x squared minus 5x minus 4. And we're going to do that, we're going to do that by partitioning 1 to 7 into 6 subintervals. So a is 1 and b is 7 and n is 6. And we're given all the numbers to plug into the function. All right, but I'm going to do what I did before and just do b minus a over n first. I just like to get that done with, because if what I also find is when you plug in all the numbers, add them together, and get a number, sometimes it's easy to forget that you have one extra step. All right, but b is 7, a is 1, n is 6, and 7 minus 1 over 6 is 1. So we have a very simple b minus a over n. Now, just like last time in all these Riemann sums, you want to plug in the numbers to your function. All right, so we want to plug in 1, we want to plug in 3, we want to plug in 3 again. So we'll only do that once and figure it out. We'll want to plug in 5 and 5 again, and then we want to plug in 7. All right, so we'll just plug these in, get the numbers, and then I'll kind of address why they can be repeated. Because it seems like if they're repeated, you should only use them once, but it's okay. All right, so plug in 1, we get 1 squared minus 5 times 1 minus 4. And what is that? That is negative 8. Plug in 3, we get 3 squared minus 5 times 3 minus 4. That's 9 minus 15 is negative 6 minus 4 is negative 10. Now, of course, we don't need to plug it in. Again, we know if we plug in 3, we're going to get negative 10. Then if we plug in 5, we get 5 squared minus 5 times 5 minus 4. That's 25 minus 25, which is 0, minus 4 is negative 4. And for the next one, it's the same thing, so don't need to plug it in again. And then the last number we need to plug in is 7. All right, and 7 squared is 49, minus 35 is 14, minus 4 is 10. All right, now why does it make sense that we can plug in the same number twice? Well, if I draw the interval out and break it down into 6 intervals, so we're going from 1 to 7, we know that b minus a over n is 1. What that means is that the next interval starts at 2, then 3, then 4, then 5, then 6, and then 7. And you can see we have 6 intervals now. Right, now 1 is the first one that we plug in, which is in the first interval. 3 is the second one and the third one, but it fits in both intervals. 3 is just the right side of interval 2 and the left side of interval 3. Then interval 4, from 4 to 5, does use 5. Same thing as interval 5, that's from 5 to 6. So similar to 3, 5 is fitting on 2 different intervals, so we can use it twice. and then 7 is in the last interval. All right, but the important point here is just make sure you use them all. Don't skip on repeats. Add all the values together. Since we have 6 here, even though they're whole numbers, let's go ahead and do it in the calculator. -8 plus -10 plus -10 plus -4 plus -4, and then plus +10. I get -26. Right. So that's all the heights added together. Now we multiply by the width, which is just 1. And this one, if you had forgotten, since the b minus a over n equals 1, you would still get it right because multiplying by 1 doesn't do anything, but do not forget that part. So our final answer is -26 times 1 equals -26. All right, but that is our Riemann sums and the definite integral introduction. Next section, we'll actually do definite integrals like we did indefinite integrals, but with one slight adjustment.